Alright, in this video we're going to profile what Project 3 is about by combining regular regression with support vector regression with a neural network based regression. So let's start with our regular regression. As you can see, we are starting here with our Gauss1 that we had a while back. This is the standard Gauss1, and I'm in this directory, which this is the Google Drive location that we have for our class. So this was the standard one. If you just run it, it comes up with this. So looking back, if you look at our, and here, I'm going to go in and remove these because these are not needed anymore. And let me run this again. Our functional value comes at 1315.8 approximately. So that's about 1315.8 as well. So I'm reasonably satisfied with that answer. I can't zoom in on this plot any, but I can on my own. And what I'm going to do is I'm going to start augmenting this code to add support vector regression to it. And then I'm going to add neural network based regression. And I'm going to just go down that path. So the code itself, if you look at it, it had the section to load in the data, which is down here. So if you look at, if you look at this code, you will see this section loads in the data. This essentially is our least squared fit. So if we had a curve and we had points, these distances d1, this z function, z is just going to be equal to the sum of all the points in there, I equal 1 to n of whatever our function was as a for each experiment minus the y sub I, and I'll square that. So these functions, I'm essentially summing those distances, which are this. This is a d sub I. Standard least squared regression. So this, in fact, is that function. If you pay real close attention to it, run over to your code right here, for example. If you come over to the example, you'll see this is the equation right here. Sorry, this is the equation minus the epsilon term, which this epsilon term is just simply the error. So this is the equation that should sit in there. Do that again. So essentially, this is the equation that should sit in there, right there. And that's the equation that sits right here. Here's the minus y sub I, and there's the squared term. As we did in class before, we can play with this as much as we want, but this is just standard least squares. What we find is we decide we're going to iterate using fmin search, which generally does a simplex method. We can even change this to iteration of 5,000. Doesn't gain us too much. 500 versus 5,000. Doubtful it gave us any more than normal. So now we're going to go down and start putting, let's first do the support vector regression under it. So okay, we're going to borrow sections of the code that we've had in the past. And we need to make sure that the functions are sitting in there. What I've done is I've quickly loaded the SVR Gauss that we worked on in class. And what we need the transformation functions. So we're going to grab the transformation function. We're going to go over here, but when we do this, we're going to say this is Gauss1 standard regression, support vector regression, and neural network regression. I'll copy it all, but before I do, let's see. I'm going to go ahead, save that, change my folder. Copy. I'm going to save copy as. Okay, so now I have my new function. And I'm going to go in. I'm going to go ahead and pull this off. And now load that function back in. I'll put this header up here. This would be support. Let's see. Example using standard regression. Using let's put it out here, SR. SVR. Network regression. Okay, so let's see. Support vector using, let's say, using SVN wide, using fast neural network. Alright, so that gives us our title. Now we're looking at the SVR section. And again, it looks like I have a save as needs to be saved on top of that. Yes. Okay, so I've got the right title here. Let's get rid of all these others. So I'm working just with these two right now. So I need to grab the transformation functions. Use those later. For SVR and NR. Okay, haven't done anything yet. Go back into the SVR, and what we will do is grab this. The functions are coming in X and Y, so I'm basically finding the minimum of the X, minimum of the Y, doing a transformation, and I do an untransformation just to look, but I really don't need that per se at the particular moment. Not in need of plotting these points quite yet. And I'm going to do these two, do the predictions. So I'm going to basically put this down. Before I go back, I need to make sure that there's no particular reason I should do this particular way. So here, I will come back in, X trans, and take that out. X trans. Okay. It just so happens that I know my data goes between 1 and 250, and it goes monatomic, and it goes by index of 1. So in other words, if I ran this code per se and looked at it at this point, I would see 1, 2, 3, 4, 5, 6, 7, all the way up to 250. So I know that's the way it exists, so that makes things a little easier. So at this point, I can plot this. Now let's check and make sure that this is okay. So up until this point, everything was the same. I'm going to run it up to here. Okay. At this point, this is the plot we have. I'm going to use the F10 key. I don't believe I can because it will stop. I'll do a step. Do a transformation. Okay. It is going to go into the wrong SVM train. So what I need to do is stop this and restart. Okay, I'm trying to get again. Oh, stepping. Just do a step. Okay, it is giving me back an error here. The reason being is because these are listed separately and in the wrong order. So let's try this again. Save it, run it again, continue. This time I get information. I should have changed this a little bit. It's probably not the best prediction, but I'm going to do a step, step, and a step. See what it looks like. Oh, I didn't clear the. All right, we're going to do a hold on. Let's do that again. Now I cleared the figure. That again. Now, doesn't look very good, and I should have used some other method instead of these dots, but I think I'll just call it blue and run it again and see what we get. Save it, run it. Okay, what we're looking at is that. That's obviously not very good. So instead of changing this, I am going to change gamma to 100. Save it, run it again. I believe it might put it on the same plot, yes. Then I might want to go back and knock this one out. And it's not doing all that good, but you can't give up yet. What I'm going to do is I'm going to go over to my website, look at my implementation, look at my options. Which one am I doing? SVM type. I am doing type 4, which is a new SVR. S4. T should be 2. That's the default, so I don't even need that. We can try to up that a little bit. Didn't work that good. Oh, it's not an NU, it's N. Okay, let's try that one. Okay, what you see, if you really look closely at this, you'll see the blue then is of course it wiggles a lot, so it's kind of overfit, but we'll take a look at that later. So in effect, we have accomplished it was unoverfitted. And again, we may keep the same plot on there. It did, so I think what I should do is go in, and the minute I open the figure, I should clear it. Alright. At this point, I'm going to put a data regression SVR, and there's nothing else there yet. So look at it. Here's our red is our data points. Standard regression is the light blue line. Dark blue line is the support vector regression. Next, we need to include neural networks. Of course, we'll have to expand the legend. Fan-based neural network. Now I'm going to make use of some of the work we've already done again. And I went over and loaded our old neural network Gauss1 we did in class. And essentially going to change up some stuff. Basically grab this, go over and drop it in here and massage it a little bit. Alright. So we do the transformation and we rename the Y to our targets. And essentially we come up and even though we don't necessarily need to do this, we're going to, let's see, transform, then we put those in there. What we do know is we do know that if we got down to here, our X-min and X-max, we don't need to create a linear distribution in space because there's already one there. And so we create this xt by transforming the linear space. But in fact, we already did that. So we can just do this, and we can remove those. Okay. So let's attempt to do that. However, let's save things first. Change the folder back to our original. Now, one of the things we're going to find is we're going to find an error message that shows up here because I haven't moved the libraries under here yet, or the MEX files. So let's just run it. We get to right here, and if I hit a step, it's going to say undefined function. So I'm going to fix that by putting the libraries in here. Alright, by doing that, let's see, I've got to create another issue. If I put that, I believe, let's try it again, step training. I may have put too high of a tolerance on it. I mean, too far of a variations, too much of a tolerance. Do a step, values out. I think, if I'm not mistaken, okay, I think, let's see, my x values, my values, I don't have any x. This should actually be a small x. Let's hit evaluate selection and look at our plot. It's supposed to be a black line big of 2. So I think that black line is it. Let's see, data. We have data. We also need to slip that in there. Copy, we'll paste that. I think now if I'm going to make one of them a certain height or width, I need to make all of them the same width. So I'm going to start by running up the page until I find this one, which will be blue. I'll find this one, which maybe I want to change that to red or something, unless I already used red. And I did. I already used red. So how about green? Save it. Run it. Continue it. Still busy. Okay. Now, I'm not sure I like the green data points because they don't stand out enough. So I decided to change them to a magenta diamond there. So let's take a close look at it. Each time you run it, you might get a slightly different result with a couple of exceptions. Let's run it again, and let's notice something. Each time we run it, give it a second, we actually get something different each time if we are considering looking at the black line. Now, SVR and regression, and of course the data, always come out to be the same. This is one of the common discrepancies or arguments about using neural networks, is that given a run, each time you run it, there is a possibility for you ending up with a slightly different answer of the neural network, sometimes good and sometimes not so good. That time it didn't appear to be that much different, but let's keep running it over and over. And that's more than likely what we will get eventually. And of course you saw the one that ran there a minute ago. Seems like right now we seem to be getting a decent one. Occasionally you'll end up with one that's a little bit off. Hopefully for the sake of showing this, here's one that is slightly off compared to the previous ones, because if you look on the plot around in here, and compare it to the previous ones, you'll see a little dip down, and a little dip down here. So now we need to know some particular way of determining whether or which one of these would be the most acceptable. In regression, that's a very common thing to do. What we do to make it more generic, and we've discussed this in class once, where we looked at an axis that went straight up and down, and this would be the predicted fit, and this would be the actual data. So what I'm saying is we subtract each one of these points from the curve fit, and we're going to plot them along the line. Now a perfect line would be 45 degrees, and all points would lay on that 45 degree, meaning that the actual and the predicted were the same. So let's go ahead and produce one of those. Now what we have to do is we have to do it for each one. So we're going to have another figure, say figure 2, in which we're going to delve into this. Let's go ahead and squish that one up, and let's deal with it here. What we're going to do is do figure 2, and we're going to subtract the 2. And we're going to make use of what we did in the support vector regression. And we're going to just simply copy this. Go back, and I think what we'll do first is we'll implement it in the support vector regression section first. Then we'll come back and implement it in the other section. I've got to find where here's where I actually did it. I do have a figure 2 already, but I'm going to put that in there in a little bit. And what we're going to do is stop here and take a look at everything that happens. And we end up right here. There. I ended up messing up because now I need to go in and make sure that I'm putting this plot on figure 1 and that plot on figure 2. So let's try this again. So we've got a figure 2 that sits here with nothing on it right now. Go ahead and drop it in there as well, so I can fold back and forth between these two plots. What I'm going to do is I'm just going to step through here. Now what I have is a bunch of z's and the y's. Do a step, but I have to bring it back up here to the step, and here's what you see. Now it looks a little funny, but you can see it's clustered along a line here. And actually it may not look like it, but it's pretty close to a 45 degree line. I think we will probably fix that here soon. But here, we're going to do hold on, xq is equal to the minimum and maximum of y. Hang on. what we have done, and I should have done it in a different color. These are the same colors. This is essentially a reference line. I think I should put it in, say, black. Do a step. The actual values ended up here, and the predicted values ended up there. Now here, what we're doing is we're subtracting the two. So what you're doing is you're looking straight down this line. Hang on. You could look at it like this. I'm looking straight down this line, if this were a straight line, as a person here. And what he sees is a distribution. If he looks down this line, that's what he sees. That's a terrible drawing, but essentially what he sees will be the difference between these two. Apparently I'm putting it in figure 4. I'd like to do it in figure 3. So I will do a histogram here. And instead of stepping, I'm just going to evaluate the selection. Here's a histogram of what this person would see as a distribution. Standard deviation. The mean, which really, if it's a perfect fit, the standard deviation would be 0. The mean would be 0, and it would be all the points would exist right here. So I'm going to drop this in here. The next thing I need to do is I need to go back and put this section in I guess in retrospect that should be 4. And this should say SVR. Whoop. SVR. Okay. Now I need to go back and do a compare here, do a copy, and then back up, do a paste right here. Okay, so I'm doing a compare, but what am I comparing against here? If I'm in this particular area, I'm not comparing ZZ, I'm comparing something different. Here, I'll show you by hitting a save. We'll run it to here. Okay, so I'm looking at this. See XP and my functions. Red, line width, and the 2. Now I should see I should not do what I did right here, because I need to have this thing 1-to-1, and that can represent a problem. Okay, so here's what I'm saying. This being XP and function, the XP could be switched to my regular X, and my function could be the regular X that I have. In other words, here, let's fix this. I'm no longer going to do a linear space to connect these. I'm simply going to say this. This simply will be X. Oops. This will simply be X, X, X. And I don't think I have any more X's in there. This should be X. This should be the function. Let's run it again. And what I'm looking at now is 250. X being 1, 2, 3, 4, 5 all the way through. Now I no longer have Z, but I have Y that I should put here. That's in C. But at that, the biggest problem I see is I'm going to have it be upset at me because of the way it's plotting this. It plots it okay there. Y and the X got, okay, I've messed up down in there, but that's okay. So I need to rotate or do this. This is the okay. Here, I better just call that predicted value. Regression. No longer subtracting it from that. I'm subtracting it from this. Okay. Save it. Run it again. Step. 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 Stepping it through. Here's my reference line. Stepping it. And this is where I should have put 3. Step. Even though it says 4, then you do another step. Look at that. You get a standard deviation of about 5. Okay. So if I run down to, say, here, where I'm inputting the fan, here's what I get now. Save it. Run it all the way through. I need to go all the way down, but I need to continue. Continue. Alright. Now, here's what I get. Figure 1 is the fit. Figure 2 is a comparison. There, unfortunately, figure 2 got clobbered. SVR started figure 2, and I should have put hold on. Let's run it again. Now, the next thing that's a problem with figure 2 is each of the data sets show up on figure 2 to have the wrong set on them. Let's see. Try it again. Alright, figure 2, the red ends up being support vector regression. The blue is standard regression. So if you wanted to, at this point, have a label on here, the thing you would do is you do standard regression, comparison, SVR. Let's save it, run it again. Here's what you get. Here's what I need to do. I need to go back and standard regression, and then say, I believe it's, I better check the help, but what I ended up putting there is the location in the southeast, so we put it down here. So the SVR looks better than the standard regression. So here's the regression, there's SVR. So the standard deviation is lower on the SVR than it is on the standard regression. You can see the distribution looks a little bit more normal here. Now we haven't completed this because we have not done the last and the best in that neural network. I said best, I shouldn't have said that, but here we'll do a comparison here. We're doing figure 2, we're going to hold on, but this time, let's not do it red, let's do it green, I guess. Let's see, figure 2, what was there a green? No, there's not a green yet. So we're just going to stop this thing and run it to here. He's calculating. Still busy down here. Alright, problem there, and that was that I should have done figure 1, run it again. Basically calculating, we're waiting and waiting. Okay, so it did figure 1, it did it there, there's figure 2. We haven't hit that one yet, but you're not basically plotting ZZ. ZZ is from the other, the support vector regression. What we need is the values. We need the values to be dropped in right here. So I'm going to start using the F9 key. So standard regression comparing SVR and call it NNR. Now let's see if this works. What I'm going to do is right click, evaluate the selection. There's the neural network regression. Now that we know that, let's see. Plot this silly thing again. We need to get rid of the first comparative. Let's go up and let's change the order of that. So we come into the first one, and we generally are looking to do off of figure 2. Instead of doing the plot first, we are going to do this one first. We're going to do the comparative first. We're going to do a hold on. And we're going to do that. Okay, so we did it that way. Next, we're going to knock out the comparatives on the support vector regression. Figure 2, plot, and we do not need this. Take that away. It's the standard predictive. And we do not, here is the values, the legend, hold on, we don't need that, and this one. This needs to be the values, and figure 5, say, for, let's see, NNR. So let's save this and run it again. It's calculating, and I have these backwards. I don't have the comparison. So I need to go back and fix that. So let me go back and fix that one first. So I'm not putting labels in this first one. I am putting labels there. So I'm going to X that out and put the labels on the last one, which would be right there. But if that were the case, this needs to roll back to right here. And I need to put this one, say, right here. Get that one. And let's run this thing again. Yes, I did a 5. Okay, so we're waiting for the fanned one. Alright. So if you look at figure 2, there should be no label yet. There's our standard regression. There's our SVR. There's our comparison. There's our actual plot. So here, let's do a step. We're over here. Now the step, so we plotted, so green values. Okay, so what we do is comparison is the 45-degree line. Standard regression is blue. Support vector regression is the red. And neural network regression is the green. Basically reproducing the labels. Next, we're going to produce figure 5. I'm going to go ahead and drop it in. And we're going to look at the title on it. So between support vector regression and neural network, the standard deviation and the mean should be right at 0 for basically normally distributed. Standard deviation here is lower than this, so from that perspective, it seems as though support vector regression won the competition. Third place and last place is the standard regression. This is the plot of the distribution. You can see the standard regression has points pretty far away from the predicted line. So again, what would be perfect is if they all lay on that 45-degree line. If you look closer, what you can see is you can see that 45-degree line, and the ones that are clustered seems to be the closest to it are the support vector regression. There's the actual curve fit, and there's a histogram looking down that 45-degree line. And that pretty much concludes this example. This is a 45-minute example using Gauss1. And so from this, you should be able to do the work that you are assigned, and we'll go on from there.